Okay, just one more thing. That basically, chemistry is top ranked. So this university has one of the strongest chemistry in China. All right, so now to the scientific part. We do machine learning and chemistry for quite some time, and there are many different ways how you can use it. So you can use it to predict properties directly. You can improve quantum mechanical methods. You can analyze data, generate new compounds. And this all can later lead to either directly like prediction of spectra or via improved quantum mechanical methods. So there are many different ways and combinations. It's basically up to your imagination, right? What you can do with it. From our side, we contributed by developing this program from 2013, MLatom, and our idea is that it should be used easily as a black box, and then you can do the typical machine learning task, but also you now more and more want to make it more as a simulation package as you would use any other quantum mechanical package. And it's all open source. You can obtain it online, or you can run it on the cloud. And we have some resources. So even if you like to do it locally on your computer, you may give a try on the cloud to see whether it fits your needs. And as I mentioned, it's quite old program, so it's from 2016. The first part was written in Fortran. Now we go into more Python way, but still the most efficient parts are important. And it predates PyTorch Central for official releases, so we couldn't rely on them on that, so we developed our own tools. And one thing of machine learning is 1 year in machine learning is basically essentially in many other fields. Maybe a bit of exaggeration, especially for quantum chemistry, but it reflects how fast the field is developing. So something which you may have heard in some talks like 2 years ago is maybe outdated right now. So that really reflects the high pace, and that's why our program also tries to follow this high pace. So now back to these different properties. So I just took a couple of examples. If you want to predict spectrum, so we can do this in 2 ways. One way is just predict the spectrum directly, so without any quantum chemistry in between. And that we can do by training on experimental data, for example, and that we done for two-photon absorption, which is kind of very complicated property to do quantum mechanically. On the other hand, we just implemented all quantum mechanics at all, just collected lots of experimental data and repeated machine learning, discovered very simple dependencies. And this property is very nice because basically you get 2 photon absorption, and then you get as a result 1 photon, which is the higher energy, so you can use it in a converting rate of photons. So that is done, and that can be used directly on the cloud. Other way to do the spectra is to predict the same way as you would do in quantum chemical. If you think about the typical way how we simulate with the absorption spectra, there are several ways. One of them is, of course, the single point convolution. So you basically optimize equilibrium geometry, calculate excitation energy, oscillator span, deconvolute it, get your spectrum. The problem is, of course, that the molecules always move. And the visual audience, I don't need to explain this, but basically you, since it always moving, you need to reflect it somehow. So this can be done by the ensemble approach, and you sample many geometries. This is standard way to get better spectrum. And it also requires oscillator spans and excitation energies, but now for many, many different structures. And many means also very computationally expensive. So we can do machine learning by predicting these oscillator spans and excitation energies by training on a smaller number of quantum mechanical points, and then it allows you to predict for millions or like hundreds of thousands of new geometries, and this gives you better precision of the spectrum. So all this procedure is done completely automatically in a MLatom. So we start with some initial, so we start with Wigner distribution, but take only 50 structures, and then we iteratively add more and more quantum chemical calculations in batches of 50 structures until we get converged spectrum. And this is very fast because we also use camera-rich regression, which is much faster and more accurate than neural networks for small number of points, as we have here a couple of hundreds of points in a thousand is not involved. And this is very accurate way because it has analytical solution. So you can get your regression coefficient analytically, and then the quality of spectra will be also quite good. And because it's machine learning, so here we have a validation set, it means we can get validation error. And if you monitor the change in validation error from one iteration to another, then you can choose when to stop adding more points because it converges at some point. With quantum mechanics, it's a bit different because even if you have 500 points for some complicated cases, it's not enough to get good nuclear absorption spectrum. So the problem is like if you have some forbidden dark modes and they only become visible because of vibration. So that means that you need to sample a lot of points to get the shape right. If you take 500 like KTB basically values, then you see that spectra can be quite different from different segments. So it's not enough 500 points. And then it also depends on the volume effect. If you use that machine learning, just train to the same 500 points, then you can get a very, very smooth and much better spectrum. So with high precision. So that's takes you some time. And here we use machine learning training 500 points to predict 50,000 points. In general, quantum chemistry can benefit from machine learning in several ways, and these are three typical ways how you can do this. So one way you can just directly learn some quantum mechanical property like energy. That's the easiest way. Another way is to improve Hamiltonian and then solve the usual Schrödinger equation as you do. Otherwise, and then get better properties. Other way to do it is, of course, to do on J function. And there are several ways how you can approach this. For some of them, we do J instead of Schrödinger, just minimize the energy. But these are three typical ways. So about this, you can read more. We just published a big book with more than 600 pages. And my connection to open Volcas is also visible from the list of authors because Roland and Ignatius and Pavlo contributed their chapter. So that's a very good contribution to this multidisciplinary book. So you can get from this book information about the background of many different approaches. As we saw, there are 37 chapters, so I'm not going to talk about all of them, but what I will talk about is how we can make this ladder of different computational chemistry methods, not just quantum mechanics, but in general. So how to get this ladder more efficient and more accurate. And in contrast to quantum mechanics, where you add more physics there, so it becomes more flow, but more accurate. In machine learning, you don't get this restriction because it only depends on the data. So it can be as accurate as your full PI, but it will still cost you roughly similar molecular mechanics, a bit slower than speed. On the other hand, currently you can benefit a lot if you merge methods because it's very hard to get very good general purpose methods in machine learning. But if you merge methods, it's much easier and more robust. And that's one of the main topics of this talk is the CASSCF approach, which does exactly this. And the benefit of using machine learning is that if you try to get more points, you will get better accuracy. So like this red line, so you always will get accuracy improved if you add more points. If you do reparameterization of empirical methods or DFT methods, doesn't matter. You will always hit some barrier because it will not tolerate. It will not improve anymore. That's the limitation of physical learning. With machine learning, there is no such limitation. And one way of combining methods is delta learning, which is kind of very simple to understand, very intuitive. That you have some bad methods like Hartree fork, which have very, very bad accuracy, but good physical behavior. Then you combine with machine learning, which has very good accuracy, but not very physical behavior if you don't have enough data. If you combine them together and just train the difference between low-level methods like Hartree fork and couple class or full CI, then these differences are usually much easier to learn. And then your predictions are better and more accurate and more physically correct. With additional cost that you need to run Hartree fork calculations, right? But at the end, accuracy will be good. Or you can also do Hartree fork if you want, and then you can stack many methods together, many models together, and then you will get pure machine learning model, which does the same. And this can be beneficial if you have a lot of data, and usually you have much more data on the lower levels than on the higher level. So you can do this for more complicated molecules, for more methods, but for this AKM1 approach, we've done very simple approach. So we argue that we want something which is faster than DFT and more accurate than DFT. Right? So if you want something more faster than DFT, then we take the empirical method, that's a straight line, that's our cheap method. And if you want to get more accurate than DFT, we want to train corrections to a couple cluster level. And that's what we've done. And then we added some default corrections because it was no network sense, semi-empirical methods were always used. So the concept is extremely simple. Now, this concept I had in mind in 2015, but see the paper published in 2021. So it needed lots of effort in many technological developments, like data, methods, and so on. But at the end, optimization of full takes 15 seconds, DFT like 30 minutes with more CPUs, and a couple of clusters at single points much slower. Right? It is much also more general than machine learning methods like any method because it can be applied. This is still quantum mechanical method. This is still semi-empirical quantum mechanical method, so it can be used for any other purposes like excited state simulations that I will show you later. There is one component which is very important: neural networks. So that was we used any neural network with small modifications to it to adjust to our purpose. Another component is an empirical method, but here we used one of the best protection elements, which is sodium-2, was specifically prioritized to treat better vertical integration energies with multi-reference treatments. And this was inherited by AKM1 method, so it's also very good for that. Then the design is all views here. So to make it really robust and applicable to different qualities. So I'm not talking about just making one model for one application. I'm talking about models which can be used out of the box like any other method is indeed for any other application. And this out of the box approach requires a lot of data. So we trained on so first of all on actually 5 million DFT points. And then when we get DFT accuracy, that's not enough for us. So we get transfer learning to 500,000 couple cluster data, and this allows us to obtain couple cluster accuracy for this approach. To do this kind of transition from DFT to couple cluster, we use this transfer learning for the so at that, there is an overview table for different properties, ground state, excited states, and so on. I will highlight the properties for each neural network was trained. Because that data set that I showed you was only ground state properties for closed shell compounds, so very specific data set. And for these properties, the new method in AKM1 has the lowest errors compared to semi-empirical or DFT approaches. So our goal basically achieved that this is more general than, for example, pure machine learning method, because if you have radicals, you can still treat it. And then the cost compared to couple cluster is much lower. So if we couldn't do this couple cluster histogram formation, here we can do histogram formation very fast today. And here is just some examples because the paper doesn't tell you actually much. But if you look at the specific examples, then you just see how good it is. So we can get the structures and compare it to the black experimental values from accurate observational spectra. And this approach gives you basically very good agreement up to picometers, right? So to with respect to experimental values. There are some exceptions like radicals, but again, for other pieces, it's very good. Then, if you go to larger molecules, it's even so much bigger here. Centi? Good. All right. So basically, if you get a big molecule, the problem was that we all trust X-ray, but then I checked X-ray values here in black and compared to AKM1, and you see there was some disagreement. And when I go back to this line, you see the triple bonds actually described quite well. So there should be no reason why AKM1 gives so bad prediction here. And indeed, we checked now with experimentalists again, and then we did better experimental measurements, and the new values and better in agreement with the AQM. So basically, we're in a stage where we can correct experiments with them. They're very fast, and there is some issues with this relief, like that's why I don't recommend to use it. So our method gets released. Then it can be applicable to chart pieces, but again, it was not really paid for them, so the machine learning part. But it's still good enough. It's better than some empirical methods. It's sometimes close to DFT is double zero. For covalent interaction, I would say it's not very close to DFT with double zero special corrections. Especially water is quite good, so that's quite impressive because DFT really struggles with that, and this method is quite fast too. Now, here is the more to this. So in the quantum mechanical methods, it's hard to judge its solidity. You don't know whether it's good or not unless you compare to some other high-level calculations or experiment. Here we get it automatically because we have an ensemble of many neural networks. So if there is disagreement which is large, then we say it's not observed. And this can be very useful. First of all, here this table is basically hits of formation. So hits of formation is extremely difficult to get as quantum mechanics. It's very expensive. And usually methods like G4 or some other methods, alternative, they're very expensive, but can get you roughly chemical accuracy, error below 1 becquerel per mole. They're quite expensive. EIQ1 is, again, faster than DFT, but gets you also chemical accuracy. And if we identify certain predictions and remove them, then for certain predictions, it has very, very good accuracy. It is so good that when we compare certain predictions with the EIQ1 for some molecules with G4 population, which are much more expensive. And if they are basically the same, but experimental values are different, then we basically say that the experiment is not good. And that's what happened here. So here experiment was really off by 4 becquerel per mole, which is quite big for our purposes. So to make it, to check it, we checked some other data sets, and we found that the revised value is actually recommended by experiment is 70.4, which is better and in closer agreement to our values. And I just need to mention that these values were used before for parameterizing the empirical method. So these errors were inherited as an empirical. Now we can fix and identify this error. So we actually can generate lots of data with this limit. Then you can use it for different purposes without it paying. So if you want to run MD, you can run one MD. Then you can get dipoles. You can get infrared spectra, which have some agreement with experiments, which is not that bad, I would say. There are some issues here with quantum effects for hydrogen atoms, but that can be solved with PIMD. Then the conclusion basically here for EIQ1 part is if you can use EIQ1 to use this relief, that's basically was my message for ground state. There are still limitations which we work on, like elements are still limited to HNO. But you can already apply it for typical organic chemistry, like if you have this big compound 200 atoms or more. We have some other systems not published in 1,000 atoms, no problem. So then it's again faster than DFT, and accuracy compared to X-ray is better. You can investigate some properties, and you can use it again for excited state calculations at here at CAF level, which can predict it fluorescence, and that works quite good. If you want to use multi-reference approach, you can also use it. And then if you do multi-reference calculations on the T's set with vertical excitation energy, then it's very similar to DDFT. You can do excited state geometry optimizations quite fast. Accuracy is again similar to DDFT. Some things are not very good, like there are some problems, but that was not in the training set of neural net. You can also run nonadiabatic dynamics, which we didn't work much about. We just run some molecule we had a line around, so to speak, and then population compared to CASSCF kind of okay to some point. Later it becomes a bit worse. We can still investigate it. You can still improve it if you want, but that was just to see that. Now for dynamics in general, we just need forces. Right? We don't need anything else. And machine learning is perfect for this. So not just the IQ1, if you want to have some other method, you can use it. So you can train any machine learning potentials models to train on forces and energies. And then the problem is that there are thousands of neural networks and kernel methods around it. Which one to use for your molecule is not clear. So to do this, we implemented typical classes like global descriptor of a molecule with kernel methods, neural networks with different descriptors like local, fixed, and beyond. So we implemented typical classes of machine learning potentials instead of implementing all of them, which is impossible. And this you can use directly in MLatom to just put here in keyword ML model type your model, and then you can test it. And we did the test for you, and the result was that if you have single molecule PS, then basically if you have forces and small trains that you use kernel methods. If you have no forces, you always use kernel methods basically. And only if you have very huge data sets and forces, then you can think about using your method. Okay, and then one of our methods related again to here Ignacio's work and Warren's work, GK. So that's a very similar formalism. We recently extended our graph models to also incorporate it. We extended it quite a long time ago, we just recently published a paper on this. And here, like another topic is which is more close to what is presented in this conference is that trajectory surface copy. So you can apply these models to do a trajectory surface copy, right? And here the additional problem is that it's difficult to learn, more difficult to learn these surfaces to get the gap correctly. Also, nonadiabatic couplings are difficult to learn. If you have low-dimensional system, it's easy to learn the couplings by including the points where you know they are fine. But in general, for organic molecules, they're just molecules bigger than simple dimensional systems, it's a challenge. There are some solutions reported in the literature, but our solution was simply not to calculate them as a low gap region and just use reference methods to do this, so it's portable. Another solution is to use Nakamura approach, which is approximation, but anyway, if you compare like the cut here to neural network potentials, you can get some quite good agreement. And then there is lots of progress in these papers again. One year in machine learning is essentially in another field, so the field moved very fast. So then all of you already now reviews about this, you can check them. So here are some attempts on some models which were used in Vienna. So we also tried to did some active learning for the surface reports. Quite good for one surface at least, and for nonadiabatic coupling, we also trained quite good models compared to literature values, but that's still work in progress. Now, one more thing is that that we can do, instead of trajectory surface copy, we can do quantum dynamics. That was basically done by my postdoc. He is specialist in quantum dissipative dynamics. But the idea is very similar. So in a way that in all the dynamics you have some property depending on the previous steps in calculation. That's why it's quite slow. It's the flow process. You can use machine learning to predict this next step. And then basically that would be repeating itself many times. So then you can do it with many different methods. We check them. The bottom line here is that you don't need all the fancy methods. Sometimes, again, kernel method works the best. So here is one fancy method which is completely wrong. So this was completely built, and this is bidirectional neural networks, so the recurrent neural networks. So that means that for machine learning, you don't always need to get the most fancy model around there. Even linear regression here works better than this fancy model. So it depends on your problem. Then the main message from this part would be that actually you don't need to do it recursive. Because, I mean, usually we do dynamics recursively, one step at a time. And then it depends on the time step. Then it also depends, so your dynamics will be different. You cannot predict something in between. You cannot predict something farther apart, so it's slow. There is no way to make it fast. It's a sequential process, right? But with machine learning, you don't need to do this. You can predict any property at any time as a function of time. So if you think about machine learning in this way, so you have some input, and how your input can be timed, and then we can predict the property, then you can get this dynamics properties directly. And this is very nice. This works. So we tested it for, again, one very common complex panel matches also like a more complex, very popular to put this like investigating like harvested complexes. And that was again quantum dissipative dynamics, and we could predict these trajectories at a function of time, even in the asymptotic limit of infinite time, because reference allowed to do this. Another way to do it is that basically sometimes you don't even need the time. You can predict the whole trajectory. That's also machine learning to do. And then you don't need to predict 1 to 3, you just can predict everything together. And if you do this, then you basically 10 picosecond block dynamics, which is may take a long time to propagate with HEM or other methods. Will take you 10 picoseconds, so it take you 50 milliseconds on the computer to get the whole trajectory for new parameters. And this is something that was done for quantum dissipative dynamics. That's why he is the package by my former postdoc. He's now independent assistant professor in Ukraine University. So he implemented this MLatom package. There are some data sets which you can play around. But we, in my group, I'm a chemist, so I'm more interested in atoms and how they look in molecules, right? So I'm more interested in these treatments that I can look at the molecule. So in quantum dissipative dynamics, you don't see the molecule. And then I wanted to extend this approach, and I still want to extend this approach to molecular objects. And if you think about molecules, you always, so chemists draw them two-dimensional. Then recomputational or theoretical chemists take on a computer three-dimensional model, but they are four-dimensional. They always move, right? So why not describe molecules in four dimensions directly? That's a much more natural way to do. And then if you do this, then again, you circumvent this, so you don't need to do this step by step. So you can just predict as a function of time, smooth, discontinuous function of time, and then basically you can get all these properties. And that basically works very nice if you compare to the traditional CDMD, but much faster. And so you can run 1 millisecond and still run it, so no problem. We done it for other molecules eventually. So here's my